Okay, we're looking at example 2 on section 5.4. This is the next one we were supposed to graph. This one actually isn't so difficult to figure out what the zeros are, if there are any. And remember, the way that we do that is we just take the original function and set that equal to 0. So if I get 4x plus 1 over x equals 0, I can move this 1 over x to the other side. I get 4x is equal to negative 1 over x. Then I can multiply both sides by x, and I'm going to get 4x squared is equal to negative 1. And then I can divide both sides by 4. I get x squared is equal to negative 1/4. Well, just looking at that, we can tell that there's no solution because you can't ever square any number and end up with a negative. So no solution here. So what does that tell us? If we don't have any solution to the original function being set equal to 0, that tells us there are no zeros of this function. In other words, it never crosses the x-axis. Okay. Also, for step 1, it says note the domain. The domain of this function is all real numbers except for 0, because we've got that x in the denominator there. So minus infinity to 0, and then from 0 to infinity. Okay, that's important because we know that if we do graph this thing, we're going to have a vertical asymptote at x equals 0. That's important because when we make our tables, we always have to include those vertical asymptotes. Okay, the y-intercept on this thing, that's what we get when we set x equal to 0, f of 0, but notice again that that's undefined, so we're not going to have any y-intercept, no y-intercept either, okay? So, in fact, what's happening at the y-axis? That's an asymptote, so that's why we don't have any zeros there. Okay, so vertical asymptote, let's go ahead and write that down. We've got a vertical asymptote at x equals 0. That's the y-axis. All right, horizontal asymptotes, we get that by finding the limit as we go to infinity. So horizontal asymptotes, I would take the limit as x approaches infinity for this function here, 4x plus 1 over x. And just notice, since we've got the x there, that limit is infinity, so we don't have any horizontal asymptotes. We actually do have this thing that's called a slant asymptote, but in this class we don't really get into those very much, so we'll just continue. So let's see, symmetry, I typically don't bother too much about symmetry. Critical numbers, let's find those. I'll try to squeeze as much in here as I can. So first we need to figure out what is that first derivative so we can find our critical numbers. So I rewrote the function like this so that it's easier to find the derivative. It's 4 and then minus x to the minus 2 power. Remember the power rule for the derivative of that thing. And let's go ahead and rewrite this as 4 minus 1 over x squared. So now if I set that equal to 0, I can move I can isolate the 1 over x squared by itself on one side. So I get 1 over x squared is equal to 4. If I multiply both sides by x squared, I get 4x squared equals 1. And then I can divide both sides by 4, so I get x squared is equal to 1/4. And then if I take the square root of both sides of that, the square root of 1/4 is 1/2. So I'm going to get x is equal to plus or minus 1/2. Okay, so these are critical numbers. Let's go ahead and set up our table so that we can figure out where it's increasing or decreasing. We'll go from minus infinity to minus 1/2. We'll go from minus 1/2 to 1/2 and 1/2 to infinity. I'll try to make this table small so we can fit everything in here. So test values, the sign of the derivative, and what is our conclusion? Okay, so let's pick negative 1. Let's pick 0 for our test value and 1. Okay, so now again I want to just figure out what is the sign of the first derivative. Here is the first derivative right here, so let's just see what happens. Actually, oops, I'm forgetting something. I can't pick 0, can I? And I'm actually forgetting that I need to include my my asymptote. So let's fix that. I said it earlier, but then I didn't do it, so let's fix that. We've got to include 0 because that's an asymptote. So let's see, I'll fix my table here. We're going to go from minus 1/2 up to 0 there. That's what we should have done. And we'll go from 0 to 1/2, and then from 1/2 to infinity. So we actually have 4 columns on this thing instead of 3. And again, let's try not to make the mistake that I just made. We do have to always include the vertical asymptote. If there is one, or more than one, we have to include them in our tables because concavity and increase, decrease, that can change on either side of an asymptote. So we'll have to actually alter this. I'll have to put minus 1/4 here, and I'll have to put maybe positive 1/4 here, and then I'll have to put, let's do 1 there. Okay, so now I've got to think about what's going to happen to that derivative when I start plugging these numbers in there. Let's start with -1. If I plug -1 in there, if I square -1, in fact, it doesn't matter whether I plug negative or positive 1 in here, right? Because what's going to happen? When I square it, it becomes positive, right? So I've got 4 minus 1. 3, that's a positive number, okay? And then notice when I plug 1 in there, what happens again? Well, same thing, 4 minus 1 is 3, that's positive. Okay, now these other ones, maybe not 100% clear, so you might want to use your calculator on this, but if you plug in -1, and again, it doesn't matter whether I plug negative or positive, because if I square it, I get the same thing. So now when I plug in, let's say 1/4, and I square it, I'm going to get 1/16, but that's going to be in the denominator. So when I divide by 1/16, I'm actually, it's the same thing as multiplying by 16. So really what I have is 4 minus 16 here. You can verify that if you like. 4 minus 16 is going to be a negative number. And again, that's really all that matters here, is that we determine the sign of the derivative. Okay, so what is this telling us? That the function is increasing, and then it's decreasing, and then it's decreasing again, and then it's increasing. Okay. Now remember, 0 is an asymptote, so all this is telling us is that it was decreasing on both sides of the asymptote. So we have to remember that. Okay, then this will tell us, since -1/2 and 1/2 are both critical, we've got a maximum value at x equals -1/2. And then again, we want to figure out what the y value is there. So -1/2, and then f of -1/2 will be the y value. Let's go ahead and write that, f of -1/2. Now remember how we do that. We take that and actually plug it back into the original function there. So if I plug -1/2 in here, let's see what happens. That's going to give me 4 times -1/2, that's -2. Now when I put a negative here, a -1/2 here, that's going to be the same thing. Dividing by 1/2 is the same as having a 2 there. 1 over 1/2 is 2. So I'm going to have -2 minus 2. So that's going to be -4. So this is -1/2 minus 4. Now I've got a minimum then at x equals +1/2. So I'm going to have 1/2, and then again f of 1/2. So now when I plug in 1/2 there, that's going to be 2 plus, now when I plug in 1/2 there, I'm going to have a +2 now. So 2 plus 2, I'll have a +4. So I have 1/2 and 4. Now this might seem a little bit strange to see that I've got a maximum value that actually ends up being smaller than the minimum value, which is maybe a little bit weird, but remember that we've got an asymptote, so that asymptote sort of divides it up into 2 different parts, and it's certainly possible to have this happen. So we'll see when we actually graph it what's going on with that. Okay, next we want, what else do we have? Second derivative, right? We've got to figure out the second derivative, and that will tell us where what the concavity is. So let's find that second derivative. I think I'll have to graph it over there. I'll leave a little bit of room for that. So f double prime of x. Let's use this. This is the first derivative here. We'll use that to find the second derivative. That's going to give us -2, actually +2 x to the -3 power. Okay, and that's the same as 2 over x to the third. Now if I set that equal to 0, notice what happens. If I multiply both sides by x to the third, well, what am I going to get? I'm going to just get 2 equals 0, right? Well, 2 does not equal 0, so what does that tell us? No solution. And what does that mean when we don't have a solution for the second derivative? It means no inflection points. So that's handy. I'll just say IP, no inflection points. Okay, all right, so all we've got, we don't have any zeros, we don't have any inflection points, all we've got is this increase, decrease stuff right here. So in order to, in fact, actually this is probably enough because we know what these y values are. So let's just go ahead and graph the thing and see what it looks like. So let me see, I'll try to squeeze that. I guess right here is probably good. Try to make this the x scale a little bit larger since these numbers are kind of small here. So we'll say this is -1, -2, 1, 2. We've got a minimum value at 1/2, 4. So about right, let's say this is 4 up here. 1/2, 4. Okay, so that's a minimum value. We've got a maximum value at -1/2. This is 1, let's say this is 1/2. -1/2. We've got a minimum value at, actually sorry, that's a maximum value at -4. Okay, now remember also that we've got this vertical asymptote, and we've got no zeros on this function as well. It turns out though that we had this thing that was called the slant asymptote. I sort of glossed it over, but what that does is it's kind of like an asymptote that does this sort of thing. For this particular problem, you might actually just want to use your calculator to help you to see what's going to happen at the end. But we know that that's a minimum value. We know we've got a vertical asymptote right there. So what the function's then going to end up doing is something like this. And then similar here. So you're totally welcome to use the calculator to figure out what's going to happen on the actual graph. Like I said, this idea of a slant asymptote, we don't really talk too much about that, but it's there. And really where you get it is you just, when we look at that limit right there, we see that as x goes to infinity, that 1 over x is not really going to do anything. It's going to go away. In fact, 1 over a very big number is basically 0. So what that means is the function is going to kind of act like this 4x, which is a linear function. That's what that actually ends up being. This is y equals 4x right there, that dotted line. But for the purpose of what we're doing in this class, you're totally welcome to use the calculator. So at least figure out what the min and max values are, what the where the function's increasing, decreasing, where it's concave up or down, etc. In fact, actually, there is one thing that we could do here for the second derivative to make this, to give us a little bit more information here. You can just notice that, say, f double prime of -1. If I notice that second derivative there, if I plug in -1, that's going to be a negative number. And then if I plug in, if I find that, I notice that's going to be positive. What is this telling me? It's telling me that the function is going to be concave down on the interval from negative infinity up to that asymptote. And you see there it sure is concave down. F double prime of 1, remember the second derivative tells us concavity. This number is on the other side of the asymptote 1. We notice it's positive there, so in fact the function really is concave up there. Okay, so I probably should have made a table for the second derivative using the asymptote as the sort of breaking value. But really, that's all you need. If there's only one place that you're concerned with, like an asymptote, or only one perhaps critical number, that's really all you need. Just pick a number to the left of it, a number to the right of it, and then plug that into the second derivative or first derivative if that's what you're looking at. And that would be enough. Okay, so again, use the calculator if you need to. It's totally fine.